All right, so last video we set up this differential equation we're thinking about from the book related to this application of a falling chain with speed v, some distance x from wherever it started to uncoil and fall through this conveniently placed hole in the table. Now this whole section is about solving exact equations. So we think, okay, this is probably an exact equation. So we're going to say step one of this exact equation problem, we have to rearrange it so it looks like an exact equation. So I'm going to rearrange, write that I'm rearranging. And say, okay, I started with xv dv dx plus v squared is equal to 32x. And then that is the same as xv dv plus, let's say, actually is equal to 32x minus v squared. I moved my v squared over. I also moved my dx over. Or x, actually I think we're used to having that. Let's see, we usually make sure to have dx up front, the thing that goes on bottom. So we'll just go ahead and move that over. So we'll say v squared minus 32x dx plus xv dv is equal to 0. Now I've gone ahead and I've taken this differential equation I was given and I wrote it in this form. M times dx minus n times dy is equal to 0. Next up, I check if it's exact. So I have, here's my m and here's my n. So I check the derivative with respect to y of the thing attached to x. But I need to remember that when I'm working on this problem, what I used to call y is now v. But conveniently, the thing that I call x didn't change. So the derivative with respect to v of v squared minus 32x, that's just 2v. And then I check the derivative with respect to x of the thing attached to dv. So that's just going to be vx. The derivative of that with respect to x is v. And I have a problem here. I checked if it was exact, and it's not. And I said that it needs to be exact for this special method we've been working on to actually help us out. So what we're going to do is we're going to fill in this 2a, 2b kind of thing. And 2b is going to be a step we use to make something exact. And I'm going to go ahead and give myself one extra slide right here for the rest of the solution. And we're going to have a quick aside about making equations exact. So we're going to finish this problem in a second, but we need an extra tool for ourselves. So I would say leave yourself, you saw how long a slide usually takes. Leave yourself that length real quick. And we're going to go ahead and write down the rule that you always need to make things exact. And then we'll also fill that in your steps in a second here. So what we're going to do is we're going to say if m of xy dx plus n of xy dy equal to 0 is not exact, we're going to need to compute a couple things. So we're going to find m sub y equal to dm dy. And n sub x equal to dn dx. That's the same thing we normally find. Right here, we did dm dv and dn dx. So we normally find that thing. I just need a notation to kind of make the formulas we're about to write easier. So note that we've just verified that my and nx are not the same thing. If they were the same, we wouldn't need this. So we're going to check two different formulas. M sub y minus n sub x over n, and n sub x minus m sub y over m. And then we're going to say that we want to find this so that either the first one depends only on x, or the second one depends only on y. Actually, I'm going to erase that squiggle because I don't think it helped. So you're going to check those two things. And whichever one works out, whichever one satisfies, it depends only on one variable now and no longer has x's and y's in it. Then you're going to use either mu equal to e to the integral of m sub y minus n sub x over n dx for the first case, or mu equal to e to the integral of n sub x minus m sub y over m dy for the second case. And if you take that mu and you kind of multiply it by your whole solution, or sorry, your whole equation, so mu, I'm going to make that mu really clear, mu times m dx plus mu times n dy equal to 0 is an exact equation. So that's what we're going to do to this example that we just started up. I'm going to also go back to where you wrote out all these steps right here. And we're going to say, okay, so step 2b is make it exact. Which means we multiply by mu equal to e to the integral of, see, it's m sub x, I think. Oops, oh, I did that thing again. M sub y minus n sub x over n with respect to x. Oops. N sub x minus m sub y over m dy. I'm just going to make sure I did not mess that up real quick before I let you keep it in your notes. My nx n dx nx my m dy. Okay, cool. So now those steps are actually complete. And so what we're going to do for our problem is we're going to try to make this one exact. And probably after we make it exact, we'll have to cut off for the next video. So we already computed our m sub v, which is the same as m sub y. That's the derivative with respect to v of the thing attached to x, so that's 2v. And n sub x is actually fine the way it is just v. And so we're going to look at those two different ratios, my minus nx over n, or swapped over m. So we've got mv minus nx over n. I like always mix these letters up. And don't worry, when you take exams and stuff, you always have your notes next to you. So that's 2v minus v, and n was vx. Or we've got nx minus mv over m would be v minus 2v over m was v squared minus 32x. So we could already see from the first one that 2v minus v is v over vx is just 1 over x. Oops. So that depends only on x, which I said, if this first one depends only on x, it's the thing you use. The second one is going to depend on both v and x, but you can go ahead and see it right now. It's minus v over v squared minus 32x. That one's no good for us. So we're continuing this. Our integrating factor is going to be that we take that thing, I'm just going to write its formula right here. Mu is equal to e to the integral of 1 over x with respect to x. And we'll go ahead and actually plug that into the problem and solve it in the next video because we're right up at our time limit here.